Thank you very much. I will start the earthquake source characterization for broadband ground motion simulation. So first part, I would like to introduce cluster earthquake application. Then I would like to introduce megathrust subduction event application. So there are a suite of scenario-based seismic hazard analysis, and the procedure is very simple. At first, we need to model source and velocity structure modeling, and then combine both using a high performance computation, and we can do the ground motion simulation. So generally, the long period ground motion is the period range is more than 1 or 2 seconds. But recently, as Rob showed, we can do the up to 4 Hertz. And the broadband ground motion simulation is combine the long period of ground motion and the short period ground motion, and we call the hybrid, usually 1 or 2 seconds. And today we focus on what kind of source is required for long period ground motion modeling and broadband ground motion modeling. The left figure is mostly done in California. And the source modeling is based on the K-square heterogeneous slip model. And the right panels are both done for Japan. And both are K-square, but very different kind of source modeling. So I would like to explain. Okay, the SCEC Broadband Platform is one of the very famous open source platform. And we can select the several methods for broadband ground motion simulations. And most models are shown as the top traces, the heterogeneous and the complex source model. And the center one is the GP model, is the K-square source model. And then today I would like to introduce the characterized source models, the code recipe. It's like a This is also K-square, but phase some modeling of wave number is like not random as GP model, like a definitive and simpler model. So today we would like to compare the GP model and the recipe performance for broadband ground motion simulation. Okay. And the similar model is like a Papajojo's group that proposed the specific barrier model. This kind of patch model is some European group used for the realistic applications. And why we choose the characterized source model, there's a behind the reason is that we would like to model very simpler model, easy to reproduce rupture directivity pulse. That's important for earthquake engineering community. As some of you are shown, like a Landers earthquake, that we can see very impact the rupture directivity pulse on the response spectrum. And also we can see similar phenomena in the 1995 Kobe earthquake. So based on these kind of lessons, there's some source modeling using the Asperity patches that can easily to reproduce rupture directivity pulses. Because rupture directivity pulse is dependent on Asperity size, like a Somerville 2003 that summarized. So this is some demonstration map of the Kobe earthquake. Assuming the 3 patches that corresponding to large slip area from the slip inversion, in the broadband ground motion simulation, the 2 distinctive rupture directivity pulse is easily simulated using empirical Green's function method. And this kind of some phenomena is confirmed by hybrid method, combining FDM and stochastic Green's function method. So based on this kind of idea, based on slip inversion, and at first we can formulate outer fault parameters of the seismic moment as a function of the rupture area. And then also we can model the inside fault asperity, like a pink area, because using some scaling law of the combined area of asperity is also the function as a seismic moment. So usually this pink area is 1/4 of the total rupture area. And this assumption is well works for the most cluster earthquake in Japan. And also we can extend this asperity part, extend to the broadband motion area up to 10 Hertz. Okay, so this kind of procedure is summarized as a recipe. And now this procedure is implemented on the SCEC Broadband Platform. So we would like to show the performance. And also this is we can see that this method is introduced as an Asperity source model as an IAEA safety report series number 85. Okay, so the concept of the recipe is that easy to reproduce, source definitively. And the second concept is to simulate rupture directivity pulses. And the third concept is that that's a calibrated empirical Green's function method that includes complexity of velocity structure and site response. Okay, so there are several methods on the SCEC Broadband Platform, and I would like to compare GP method and some here recipe method. And this is some performance of the recipe, assuming 1D velocity structure and 3D velocity structure for magnitude 6, some strike slip event, and also deep slip event. And this is some trial of the SDSU case and same earthquake. And this earthquake is occurred on hard rock site, and this earthquake occurred very deep, some soil site. So we can see that some difference of the 1D velocity structure performance and 3D velocity structure performance. In this period range, we can see similar performance, and some recipe can robust for the either 1D or 3D velocity structures. And also another work done by Pitarka et al. 2017 is we can compare the recipe and the GP method. And the source model itself is a very different way, but once calculated the near fault ground motion in velocity, the red line from GP and blue line from recipe is mostly the overlapped, even near fault ground motions. And this is some bias plot. And recipe has a little bit underestimate a period range of 1 to 3 seconds, and that can recover if we increase the rupture velocity over the asperities. And following the study by the Pitarka et al. 2020, the Kumamoto earthquake application, and we can see the recipe and the GP and both hybrid show the nice performance, even they assume the 1D adjusted velocity model. And this is a near fault ground motion, and also this is a finite offset close to default. And I would like to mention the Kumamoto earthquake is similar to the Ridgecrest earthquake, that we can see clear surface offset and surface break. And this model is top depth of the fault is 0 kilometer according to the paper. And but they naturally model the even recipe source or GP source. So this kind of how to model the shallower part is very important. And there are dynamic approach by another work, and there are still discussion what kind of slip velocity is required for the shallower part, and still on the way for the research. But maybe direct observation would be necessary in the future. So my proposal is like a safer, we need to measure the drilling in the future, and like an on-fault seismology is necessary to understanding this kind of phenomenon. Okay, so I will move to the megathrust source modeling. There are a lot of the variation with the megathrust source modeling because usually the distance to the source to site is rather longer than the cluster earthquake. And we don't have a station on the offshore. So there are many approaches like a patch model or like borrowing the Sumatra event to the some paced up to the cascadier, or a completely random model, or like a hybrid model. But the recent magnitude 9 plus earthquake taught us the very different view of long period ground motion and short period ground motion. And this is a Tohoku example of the long period source, the slip inversion using the longer than the 10 seconds. And we can see the center part is a large slip, and some slip is very close to the trench. But the general view is similar. And this seismic moment is, of course, it's reaching to the magnitude 9 plus. But if we do the broadband source model from 1.1 to the 10 hertz, we can some estimated patch is the down deep edge, or some partially overlapping to the large asperity. But generating seismic moment is just magnitude 8 class. It means that maybe GMP for megathrust will bound close to the 8.2 or 8.3. So we need to solve some discrepancy in the future source modeling. And a similar phenomena, we can see the Maule earthquake 2010 Chile, like Frankel already explained. Some left figure is a slip inversion longer than 10 seconds. And short period modeling is called sub-event modeling, like this kind of characterized patch. And this magnitude is, we can see around the magnitude 8 plus. And also this GMP is saturated close to the magnitude 8, indicating the similar phenomena of Tohoku. So recently some application to the cascadier, like a magnitude 9 plus heterogeneous patch, and some sub-event patch for magnitude 8 plus is already applied by USGS. So, but this kind of modeling is we need to measure the uncertainty. So this is an example of using the characterized source model for the Nankai megathrust earthquake, and for the different source region or different asperities or different rupture starting point, and a series of numerical simulations result. And we can see the huge range of the spectral velocity. But if we cluster by the smaller event case, mostly we can see the normal distribution of the PGB, but only megathrust maximum cases is a very like an outlier. So we need to care about this kind of uncertainty treatment. Okay, but finally, we need to wait offshore observations, because now the cable type observation of some already prepared for the seismic observation, and also geodetic observation is frequently done by this kind of way. So this kind of observation may constrain the question of the magnitude 9 plus long period and magnitude 8 plus short period in the future. Okay, so to conclude, the broadband source modeling for cluster earthquake is well summarized on the SCEC Broadband Platform. So validation for 1D and 1D and 3D velocity models show a reasonable performance. And the recipe for predicting strong ground motions targets the reproduced ground motion pulses that are important to the earthquake engineering. And the shallow source modeling needs deep borehole observation that capture slip velocity directly. Offshore observation may constrain magnitude 9 plus long period and magnitude 8 plus short period megathrust source. Thank you very much.
Thank you, Hiroe.